Hello everyone. If you can see me and hear me, if you don't mind, can you just please leave a quick indication in the chat that you can see me and hear me okay. This is my first stream of the year, so just making sure everything looks okay. Awesome. Thanks, Naomi. All right, so welcome to Chemistry in Our World. My name is Dr. Matt Lukeman, and I am a member of the Department of Chemistry now. That's great. Thanks, everybody, for weighing in. At the moment, I can see we are up to 224 people, which is good. That's certainly the majority of the course, which is awesome to see. On this first slide, basically, I just have title of our course and some information about me, contact information, what my email is, what my phone number is, where my office is if you need to get in touch with me. The best way to get in touch with me is by email, as you may have guessed. But yeah, you can try me by phone or pop by my office if you like, if you're nearby. For this course, office hours are a funny thing because I have a lot of people in this course, and trying to find a block of time that is going to work for this number of people is just craziness. So what I'm doing for office hours for this course is if you want to talk to me, just send me an email and we can set up an appointment time on a person by person basis. So you're not going to be restricted to when I'm actually going to be physically in this space for a certain set number of hours. Especially now that we are going online for at least the first 2 weeks, appointments are probably going to have to be scheduled anyway because they're going to likely be over Teams. So yeah, if you, yeah, that should make sense. Hopefully that's clear. Now, I want to tell you a little bit about myself. I obviously am a prof at Acadia now, living in Port Williams, just outside of Wolfville. I grew up in Antigonish, Nova Scotia, which I know for a lot of people is the enemy right now, but it's not such a bad place. So I grew up there, and I went to St. X, and I got my degree there in chemistry, an honors chemistry degree. That was a long time ago. I graduated in 1999, so last century. This is a picture of me, and see if you can guess which one of these four I am. Okay, I'll take the guesswork out of this. I'm number 2 with the blue matching outfit. On the far right is my brother Ryan, who is a professor right now at St. X in the math department. So there's 4 of us, 4 brothers, and we grew up there. This was my graduating chemistry class from St. X back from 1999, and I'm in there somewhere. I'm second row in the back. Second in, and second row from the back. So what's interesting then, as is true now, it seems at the undergraduate level for sure, chemistry degrees have a lot of females in them. So for my graduating class, there was 5 males and everybody else here was female. So very interesting to see that gender split. I finished my degree at St. X, and went to graduate school, and I went to the opposite side of the country to the University of Victoria. There I see somebody's guessed correctly which one was me. So I went to the University of Victoria, UVic, and you can see where that is. Okay. We're still together here. It just gave me a critical failure warning, but we didn't fail, so I think we came back from the brink. So yeah, I went to UVic on the opposite side of the country, and UVic's a beautiful campus. It looks like this. You can kind of see there's a big kind of circular road, which they call Ring Road, and all of the campus buildings, or almost all the campus buildings, are housed within that big ring. You can see it's close to the ocean there, the Pacific Ocean, and a very beautiful campus. When I was there, it was very well known for having rabbits everywhere, and this was not an uncommon sight. The building in the background there, by the way, is the chemistry building, and you can see there's just rabbits all over the place. And I believe these are like domestic rabbits that people had as pets that they abandoned on campus. And rabbits, as they will, multiplied, and they were they reached nuisance level. And I think they may have started programs there, or maybe completed programs there, to reduce or eliminate the rabbits from on campus. All the buildings are connected by underground wires, and they were like digging holes and chewing wires underground and stuff like that. So they found a solution, I think. I don't know exactly how. Yeah, we've got vicious crows, that's for sure. Rabbits are a little bit cuter than crows. I used to feed them, used to contribute to the problem, and yeah, they're pretty cute. Went to the University of Ottawa afterwards, and the University of Ottawa is quite a different campus. It is extremely condensed. This is, I think, like a kind of an artist's rendering of the campus, and I think this rendering has more trees than actually existed on campus. It was very urban, concrete, condensed, and goes right along the canal that you can see running along there, which was actually really nice because it froze in the winter and you can go skating. And from one end of the canal to the other, I'm not sure how many kilometers it is, it's like 12K or something like that. And so yeah, you get to see, you get that at least in the wintertime. This is a picture of my group that I worked with at the University of Ottawa, and that's me at the very, very back, kind of partially obscured, and we were at some dinner somewhere. Then got the job from the University of Ottawa at Acadia. I flew here to do the interview. Actually, we had a snowstorm during my interview that closed the campus, but we pushed on anyway. Got the job. Now I'm here back at Acadia. So this is me when I first started in 2005. This was my first research group in my first summer, and that was 17 years ago. Wow. So I was, I think, 27 when this picture was taken, when I was first new at Acadia. All right, so that's me, that's who I am. I'm here now. I've been head of the department for the last 6 years and just finished being head at the beginning of this month. So we have a new head now, Dr. Vlad Zamlini. And I have this is coffee, by the way. It's not a stout or anything like that. Keep me going. So I'm going to talk a little bit about the structure of the course, how it's going to work, how you're going to hear from me, how you're going to get information. First of all, Acorn is going to be your primary resource. Acorn you should probably be used to using by now. I will be posting all of our lecture slides on Acorn, so everything that you see on the screen here will be available there. For the entire semester, this option that you are experiencing right now, this online version of the course, you will be able to experience that all semester if you like. This course is large. Currently, it's at 325 students, and on top of that, there's another dozen or so on a waiting list hoping to get in. So when everybody is in the course, we are going to have way more people than the largest classroom on campus can hold. And so what I'm going to be doing is offering at least this online option at least all semester. In a couple of weeks, when the the online mandate is lifted, there may be a hybrid option offered at the time as well. Maybe not. I have to wait and see how things are looking, but certainly I'm not going to force anybody to come to a big class packed with 300 people, certainly as things are going right now. So what that means is the link that you followed to get here, I sent in an email. In the future, these links are just going to be posted on Acorn. So you can go to our Acorn page, click the link, and it'll take you straight to the stream for that class. Also, the same link after the stream is complete will bring you to a recording of this stream. So this stream is being automatically recorded, and you can come back and see this anytime you like. You can play it on 2x if you want, speed it up, whatever you like. Just wanted to let you know that this online option will be available to you all semester. And I'm not going to email links for every class. I'm going to post them on Acorn, and you can go find them there. So either follow it through Acorn, Or what you can also do is just subscribe to the channel on YouTube, and then you just know when class time starts, log in, go to YouTube, appear at the right time. I find YouTube is a more convenient platform for giving a course like this with this large number of people, because with this many people there's really no meaningful discussion anyway, and that's, I think, what gets lost moving from Teams to YouTube is the discussion part. But since we're not really doing discussions anyway, you can still certainly ask questions and leave comments. I'm staring at the chat right now and kind of keep my eye on it throughout the whole thing. So if you have any questions or comments, anything you'd like to see addressed or whatever, please put them in the chat, and that's going to be the easiest way to get them to me. Wonderful. I may also put on Acorn other random pieces of information. There could be links to articles, assignments, links, descriptions, all of that stuff will also go in Acorn. And also the other thing is important announcements. So at the top of Acorn, somewhere I have this here, yeah, the very top of our Acorn page, which looks like this at the moment, you can see that announcements button right at the very top. What that is a tool I use to email the class. So anytime I send an email out to the class, I send it through that. What that means is if you miss an email or delete an email or whatever, what you can do is go back to announcements here and see a full record of all emails that I've sent to the class over the course of the semester. So that way you will never miss a class. Great. This is going to be the grading scheme I'm going to be using for the course. You can see we have unit assignments. There's going to be an assignment for every unit that we cover, which will be around 10 to 12. And this is going to be worth 50% of your grade. There's going to be 2 assignments, one written and one video, worth 15% of your mark each, as well as a final exam that's going to be worth 25%. What you'll notice is the total of all of these adds up to 105%. And so what I will do when I put the marks together is find the component of your course, one of these 4, that you did the worst on. And whichever one you did the worst on will drop in value by 5%, so that the total will become 100. So if you blow the final exam, it becomes worth 20%. If you forget to do the unit assignments, it goes from 50 to 45, etc. So these unit assignments actually, I'll talk a little bit more in a minute, but that's 50% of your grade, which is a huge percentage. And that basically is a grade that is given for you remaining engaged throughout the whole course. The grading scheme I'm using, I don't really need to post this anymore. I think this has been approved officially by Senate, but anything over a 90 will be an A+ in the course, 80 to 85 is an A, and so on. You can see all the grade ranges. All of the grades I'm giving you in this course are going to be percentage grades up until your final grade for the course at the end. So I'm just going to be using percentages all the way through, and then once the percentage is calculated at the end, I'll convert it to a grade and post it. All right. Are people still with me online? Everyone's happy? I just see no action in the chat, so just let me know that you're still alive, because if I know that you're still hearing from me, yep, that's good. Yeah, that's just keeping me sure that there is a good connection here between me and YouTube and whatever. All right, let's keep going then. Thanks for everybody for popping in there and letting me know. So these unit assignments that I've been talking about, these unit assignments that will form 50% of your grade, there'll be 1 per unit, there'll be mostly multiple choice questions, and what I'm going to be doing is posting these questions in quiz format on Acorn. They will open prior to the class that covers that material. It'll remain open for roughly a week after the material has been covered. I'm not going to give extensions to these. Don't forget about them. Don't forget to do them. The best thing you can do is open it when the class starts, follow along with me, and answer the questions as they come up. It'll be very straightforward. If you do that, if you just open Acorn when the class starts, answer questions along with me, basically there's no reason why you shouldn't get a 50 out of 50 on that part of your grade, which brings you quite a bit on the way. These are open book. You can find any resources you want. I do ask that you do them independently and don't copy these off of somebody else. Each assignment will have different numbers of questions, and that means each assignment will have different value towards your final grade. So if you have an assignment that's that has 5 questions versus an assignment that has 10 questions, the 10 question assignment will be worth double. So don't think of it as getting a grade per assignment. Think about it as getting a grade per question that you answer. My goal is to have around 100 questions for the entire semester. The first unit assignment is already up. It is called Unit Assignment 1, and you can see that on our Acorn page right here. This was a snapshot of our page from a while back. It's been updated a bit since. You can see the class link to this class is there. The same link will bring you to the recording after. Below that, the unit assignments, you can see the first one is available there for Introduction to Chemophobia, and the first assignment has a total of 5 questions. So it's a bit of a short one, kind of get you used to it. So once the assignment is open, are we able to go back whenever? Yes, so you can open it and do part of it and then save your progress and go back. You can enter and exit as many times as you want. The unit assignments are not time limited. So, feel free to take a peek, go check them later. If you have any issues with your unit assignments, please let me know. The most common thing is you can manually submit them. Occasionally, people will accidentally manually submit before they do them. If that happens, just let me know, and I can fix that issue for you. PowerPoints will go up there as well, and I think if you actually go to our webpage as it currently looks, our first set of slides that this is included on is now posted there as well. So this is what the unit assignment questions look like. It says, what percentage of your final grade will the unit assignments be worth? So this basically is a question of, read our course descriptions. This should be an easy question if you're listening right now. The answer is 50%. Yeah. Another thing that I'm going to be doing for this course that I want you to be aware of is I have an Instagram account that I've been using last semester for organic chemistry, and I usually use it for Chem in Our World as well during the winter semester. And basically what this is if you subscribe to the Instagram account, and you can see the account name there, Ochem Lukman, what this account will do, basically it'll pop up questions every so often. I'm not going to commit myself to any certain number of questions, but it'll have relevant questions every so often to the course material that'll pop up as Instagram stories, and it'll have a little quiz like you can see there on the slide. And they're just for fun. You can click whatever answer you want. You get little fireworks when you get it right, and it buzzes your phone if you get it wrong. I'm not keeping track of these. I'm not tracking who's doing them and who's not. It'll not be a part of your grade or anything like that. It's just sort of a little fun thing to get some additional chemistry into your, I guess, daily feed, daily lives. I got a question from Sophia. Will we know the assignment dates in advance or on a week-to-week basis? So basically, they will open when we start the unit. So when we start a new unit, when we start them in class, that assignment is going to be open. And I'm not going to be sending reminders when they close or open, but what I will do is when they do open, when they appear on Acorn, and I'll go back and show you what that looks like. So when they appear on Acorn here, you see where it says Unit 1, Introduction to Chemophobia. After the title, what I'll do is when I've settled on a due date, I'll write the due date in right there. And it'll be 1 week after I write that in. question is, do we get bonus assignments for completing those? And those, I assume you mean the Instagram questions. And the answer is a hard no, and the reason is because I don't want to have to monitor these and count them up. Instagram has a way of, well, first of all, too, it would be difficult for me necessarily to identify who's who based on your Instagram account. And no, so yeah, these are just for fun. Go to this Instagram account, subscribe if you like, and if you don't like or not on Instagram or whatever, don't worry about it. There is no textbook for this course. Everything that you need, I'll provide, and if you feel like you need something else, you let me know and I can point you to resources. Academic integrity is a sort of a boilerplate thing I talk about in every one of my courses. This is especially important in this course, especially when it comes to not the unit assignments, but the other two assignments. I shouldn't call them both assignments. I should call them unit quizzes or something. I don't know. But academic integrity is taken very seriously in this course. Your first assignment, when you complete it, will be basically writing a short paper, and these are you run through Turnitin. And Turnitin is obviously it detects plagiarism. Every year, despite multiple warnings, I always get 5 to 10 people that are caught red-handed basically by Turnitin. Please, 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 please do not copy from other materials without giving credit. Do not copy off of somebody else. Do not try to submit somebody's assignment from last year as a this year's assignment. I get that sometimes too. These are all generally easy to catch, and please don't make me have to do something like that. Logging into Top Hat remotely, you can ignore that part. Top Hat is a platform I used to use in this course to track attendance. With an online format, it doesn't really work as well, so that doesn't seem so useful anymore. So don't worry about Top Hat. You don't need to actually pay anything for this course. You don't need to buy a subscription to anything. You don't need to buy a book. You don't need to buy anything. So it's a free course besides what you paid for tuition. All right, so in terms of topics covered, here's where we're at. We have our first unit, which we're in right now, which is an introduction and chemophobia unit. We're going to do a unit afterwards in toxins and toxicity and how to think about substances in our environment, chemical substances. We have a short one on the scientific method and elements of chemistry, which is more a history or background of where chemistry came from and has arisen from. We have a few units on different types of pollution, of air pollution in particular. The other one is ozone depletion and then global warming. Units on water, units on chemistry of cannabis, plastics, pesticides and herbicides, and food chemistry. And I have a kind of thing where I don't like teaching the same thing all the time. So if I get time and if I get inspiration, sometimes I'll X out a topic and add a new one. There's a number of topics that I used to teach in this course that have long since disappeared. There was an interesting one on nuclear chemistry. There was one on electricity, batteries, stuff like that. Anyway, as my interests move, the topics covered may move as well. So you're likely to get the first 10 to 12 of these, but there could be, some changes as we go. That dog is indeed chemophobic. All right, so we're going to start a short unit now on chemophobia. Usually with an hour-and-a-half class, I don't like to just do the syllabus and then run, especially since I got you all to meet here and join with me online. And what I want to do is start off with this picture. This is a picture of a bag of coffee from Just Us. This was their old packaging on the left. They now have new packaging that you see that looks more like what you see on the right. But what it would say on the back of the bag for the old packaging, I haven't actually checked the new packaging to see if it's the same, is it claims that their coffee is full-bodied, earthy, and chemical-free. And this is a very interesting claim. This idea that the coffee is chemical-free is a not uncommon one. You see this sort of claim being made all the time for various products, whether it's, personal care products, paints, anything you can imagine. People like to claim that their product is going to be chemical free. Now, I'm a chemist. I think about the world in terms as being made up of chemical substances. And to me, the idea of chemical free is kind of ridiculous. Like, if I hear something is chemical free, what I think is that, it's empty space, right? Because I would consider air a chemical, water a chemical, coffee beans certainly a chemical. So this bag of coffee that's claiming to be chemical free, I would view that as an empty bag. But that's obviously not what they mean when they write it on their bag. What do they mean when they say the product is chemical free? And that actually is open to some debate, because there's a number of things it could mean. It could mean, for example, that the coffee was processed, like nothing was added in the processing to the coffee, nothing to keep it fresh or preserve it. It could mean that the coffee was grown without any pesticides. It could mean that the coffee was grown without any chemical fertilizers. It could mean all of those things, or it could mean none of those things and it's chemical free in some other way. So the idea that this product is chemical free, to me, when I see chemical free, it's more sort of a throwaway marketing thing, because it doesn't really have a meaning, a certain meaning. So this stems, though, from the idea of something called chemophobia, which means fear of chemicals, and the idea that we should be afraid of chemicals. And chemophobia, it's not afraid of chemistry as a discipline, right? That's a different thing. Some people are afraid to study chemistry. And if that is you, I hope that you aren't afraid to be taking this course and that you enjoy this course and don't find it too daunting, right? The course is designed, by the way, so that you do not need any prior chemistry education. You could have never taken chemistry in your life, and hopefully you can learn a lot and get a lot out of this course. So here's an example of chemophobia. This is a chemistry set that you can buy. I don't know if you ever had one of these as a kid. This says 60 fun activities with no chemicals, which makes me wonder, why would you want a chemistry set unless you're working with chemicals? All right, so we have an Instagram account for the course. As I mentioned before, I'm on Facebook and Twitter and whatever else. And the interesting thing about social media is it allows kind of anybody to present an opinion or a viewpoint without really going through any kind of editorial scrutiny. So you can see all kinds of things pop up in your feed. People will share it. It can be true, to quote Donald Trump. It could be fake news, and there's certainly plenty of that out there as well. And that can have a very large harmful effect on society, but actually for me it's a good thing, because it gives me a ton of information to talk about in this course. And what I'm going to talk about now in particular is one such article that was shared with me years ago on Facebook, and started with this image, 7 toxic reasons to ditch dryer sheets. And you can see there's a person there wearing kind of like a hazmat suit with their laundry. Doing laundry may be hazardous to your health. And you may have seen, maybe not this one, but 1,000 other articles just like it, claiming that we need to be worried about some chemical substance that's in some product that we use regularly. So I was interested by this one. What's so bad about dryer sheets that they're complaining about that we need to be worried about? And this was the list. These were the 7 reasons. The 7 reasons were 7 chemicals: alpha terpineol and benzyl alcohol, camphor, chloroform, ethyl acetates, and so on. And for each one of these, what they talk about are all of the negative things that you can experience if you're exposed to these chemicals. So the first one, causes central nervous system disorders, loss of muscular coordination, central nervous depression, headache. Benzyl alcohol, a lot of the same things: vomiting, dizziness, central nervous depression, in severe cases, death. The next one, we have chloroform. It's neurotoxic, carcinogenic. Camphor causes dizziness, confusion, nausea, twitching, and all these sorts of things. So this is a very interesting article, and it brings me to kind of my first point I would like to make about this course. I looked at all of these chemicals when I read this article the first time, and as an organic chemist, as a trained organic chemist, I looked at this list and I said, I recognize several of these chemicals that are on this list. The first one, alpha terpineol, is a natural product that's produced by lilacs. And in fact, it's the chemical produced by lilac flowers when they're in bloom that gives rise to their characteristic smell. And so if you go out in May or June, whenever they bloom, sometime around then, it's early, and you walk outside and you get that nice floral bouquet smell, that's alpha terpineol, along with some other accessory chemicals that you're smelling. Benzyl alcohol is found in jasmine flowers, and if you drink jasmine tea, you're going to be drinking some benzyl alcohol. It's present, and if you smell the flower, of course, you're inhaling that compound as well, so you're getting that put into your body too. You can see this one is camphor, and camphor is found in, what's that stuff called? It's not rosemary. Maybe it is rosemary. Yeah, rosemary. It makes up something like 15% of the dry weight of this material. So if you took this herb and you dried it out and separated it out, the camphor is like a major component of this. Same thing, ethyl acetate is found in wine. It's in fact the chemical in wine that's responsible for the fruitiness of wine. So more ethyl acetate is found in wines that are considered more fruity. And linalool is found in many different types of flowers, and it's another sort of floral smell. So all of these compounds, are certainly naturally occurring compounds. And I remember looking at this and thinking like, okay, well, these are all natural. Why should we be worried about these being used in dryer sheets? And maybe a good question at this point is, first of all, why do you think these are used in dryer sheets, period? And if you look at the list of these substances where they're found, it's probably because they smell good, right? These are all nice floral smells. These are all added to dryer sheets to make your clothes smell like flowers, make your clothes smell good as well. Clearly, if you went up to that bunch of purple flowers, those lilacs in the very top image, stuck your nose in the middle of there, and drew in a deep breath, deep smell, and sniffed those flowers, you're not going to have loss of muscular coordination, central nervous system depression, or a headache. If you go to those jasmine flowers and you make a jasmine tea and drink it, you're probably not going to have vomiting, dizziness, and death. However, I'm going to say this. Every sentence that's written on this slide is actually true. All of these things are negative side effects that accompany each one of these chemicals. So what's the difference? Why is it true that benzyl alcohol can cause death, whereas these flowers don't pose any particular risk to you? And the answer is that, benzyl alcohol, if you purify it and drink a liter of it, you probably will die. But that's very different from smelling the small amount that is produced by a flower. Same thing with ethyl acetate. If you drink a glass of wine, the ethyl acetate is going to cause you no harm. But if you were to inject 20 milliliters into your bloodstream, well, yeah, that's probably going to kill you or cause some really horrible negative biological effect, right? So this article, what it gets right is all of these complaints associated with each one of these chemicals. What it gets wrong is the risk that the dryer sheets are posing, because what it's missing is the dose. First of all, the amount of this substance that you're being exposed to, and second of all, how that exposure is actually taking place. All right, I got a quick question here. The quiz questions correlated in order with how you're teaching? No, they're correlated directly in order. In fact, they will appear as slides in the slideshows as we go along. Wonderful. So that brings me to the next kind of point where we have, obviously the dose is gonna matter and the route of use matters. An example here is potassium chloride. And potassium chloride is an ingredient that you can see here in Dasani water. So you go buy a bottle of water, you can see it's made from purified water. It's circled there in the bottom right. It's kind of small, but it says potassium chloride is added. Yet potassium chloride is also used, injected into somebody's veins as a lethal injection technique. So in places that have the death penalty, one of the ways to bring about that death is lethal injection by using potassium chloride. Clearly, you don't have a risk of your heart stopping just by drinking the small amounts of potassium chloride that's in the Dasani water bottle. So these differ both in the amounts and in the route of exposure. Directly into your veins is quite a bit different than drinking it orally. Or there's lots of other ways to get substances into your body as well. You can have it absorbed directly through your skin. You can inhale something. There's probably some other methods that we probably shouldn't talk about here. So here we go. We're going to be introducing, as the course goes along, we're going to be introducing a number of important ideas in chemistry that's going to guide us on our way through. The very, very first thing that I want people to understand is that matter is made out of atoms. Okay, so we have table salt there. Table salt forms little cubes. You can see the micrograph there on the right. If you look at salt under a microscope, you see all these little cubes. These cubes are made from sodium ions, so positively charged sodium ions, negatively charged chloride ions, and they form this three-dimensional structure that you see there, alternating positive, negative, positive, negative, positive, negative. And so what this does, we call this a lattice, and it's because they arrange themselves in this cubic shape that the actual salt crystals at the end of the day look like cubes as well. It's like that small shape that are like, growing on themselves. So matter is made from atoms. Not only that, two atoms will be identical with each other in every way as long as they have the same number of protons, neutrons, and electrons. So what that means is if you find a carbon atom that is found in a tree, for example, that's identical in every way to a carbon atom that you find in crude oil or a carbon atom that you find on an asteroid out in space. As long as they have the same number of protons, neutrons, and electrons, they have the exact same structure, the exact same behavior, and they're completely indistinguishable from each other. So here is a question. This is, I think, question 2. Which subatomic particle is not found in the nucleus of the atom? We have electron, protons, and neutrons. The protons and neutrons in the atom make up the nucleus. The electrons arrange themselves in things called orbitals that surround the nucleus, so the answer to this question is electron. All right, so we have the idea that all matter is made out of atoms. All atoms are identical to each other when they have the same number of protons, neutrons, and electrons. So next what we have are molecules, and molecules are larger structures that are made up of two or more elements, or two or more atoms. And so when you construct a molecule, basically what you're doing is you're taking different atoms, you're bonding them together. We're going to talk about bonding later in the course, and you end up with a molecular structure. In chemistry, we have multiple ways of representing chemical structures, and on the screen right here I have one such representation. This is one that you would see if you took organic chemistry. This is called bond line structures, sometimes called skeletal structures, and it's the structure of a molecule that's found in vanilla, natural vanilla, called vanillin. And vanillin is produced naturally by the plant, and it's the compound that's present in vanilla that is responsible for the smell and flavor. If you had a container of pure vanillin, you would recognize instantly what this substance is by its smell. So two molecules are also going to be identical to each other as long as they have the exact same atoms bonded together in the exact same arrangement. So this is another belief in chemistry. This is another sort of fundamental assumption that we make in chemistry, that one molecule will react identically, interact with biological systems identically, everything will be identical about it. There's no difference that we can detect between two molecules if they have the same atoms in the same arrangement. That means the behavior of the molecule depends on its structure, not on anything else. So here's what we have, and I see the comment, vanilla smell comes from beaver farts. I actually am going to directly talk about that in a little bit. Beavers and their relationship with vanilla. It's not quite vanilla, actually. My coffee's starting to get cold. Time to speed it up. Okay, so vanillin can come from either a natural source, you can grow the vanilla plant, or you can get it from an artificial source, you can make it from a lab from crude oil. I'm going to hold that, in chemistry would say the same thing, these two molecules are identical, absolutely identical in every way, even though they've come from two very different sources. And there's many online places that'll tell you you should always only get a naturally sourced thing. But in terms of the difference between these two, there is none. There may be a difference in terms of the processes, in terms of maybe like environmental impact or something along those lines, but in terms of the actual final product, you actually can't distinguish the artificial from the natural, assuming all else is the same. All right, so when you go to the store and you want to buy vanilla extract because you're making a cake or something, you can choose either natural or artificial vanilla extract to purchase. I'm going to say right now that the active ingredient in both of these is vanillin, and the molecule is identical coming from the natural and the artificial source. They're the same in every way. What difference do you notice if you go to the grocery store and see the two? Well, certainly one difference is in the price. The natural vanilla extract it can be like 10 times more expensive. It's quite a bit more expensive. I'm just going to grab one thing for 1 second. I should have had this ready, but all right, I'm back here now. I have, here it is. Great, I'll bring those up in a sec. All right, I'm ready again. Natural vanilla comes from a plant. The plant looks like what you see there on the left. It's kind of a viney kind of thing. It grows, typically it's supported by some other structure, like it'll grow up the side of a tree. And the growth of this thing, it produces these long pods. And you can see the pods on the left picture, they look green. On the right structure, they kind of look like a big elongated raisin. And I have two of these right now. I can show you. I don't know, too close to the camera maybe, but they kind of look like a bean kind of thing. And yeah, you can buy these and you can make your own vanilla extract if you buy the actual pure vanilla pods. You just soak them in a source of alcohol like vodka, and they'll extract, and you can get your own natural vanilla extract that way. So once they're dried out, they look like the thing you see on the right. What's happening chemically during the ripening process, I've drawn in chemical structures in the bottom. I am not expecting people to look at these structures and identify exactly the processes and what's going on here. If you've taken organic chemistry or biochemistry, this might make more sense to you. Basically, all you really need to know is that there's a larger molecule in the unripe beans, and as it ripens and as it turns brown, this molecule splits in two. And you can see the two molecules are formed as products there. The right-hand product is vanillin, which is responsible for the vanilla smell. And the left-hand structure is glucose, which is a sugar molecule. So this is how it's grown. It turns out that the vanilla plant is actually extremely finicky when it comes to the environment it wants to grow in. It will not grow, for example, in Nova Scotia really well at all, maybe if you're in a greenhouse or something like that. But there's only very certain climates that are well suited to growing vanilla. I believe some major percentage of the natural vanilla in the world is grown in Madagascar. So it's like one of the major sources, and that can give you an idea that very warm, almost tropical environment is likely best for that particular substance. So it's not easy to grow a lot of it because it is so dependent on the environment. You can't, for example, go to Saskatchewan and grow hundreds and thousands of acres of fields of this stuff like you can with something like wheat or corn. So it makes this stuff quite expensive. I'm asked if we're going to have to draw these structures. That's a hard no. I don't expect you to even recognize these structures, let alone draw them. Another question, due to the biochemistry of our body, do we process them in the same way when we consume them? Absolutely yes. So if you take a substance into your body, whether it came from an artificial source or a natural source, your body also has no way of knowing what the source or history of that molecule was. It'll treat them in identical ways. And this, by the way, is the basis of modern medicine, because most modern drugs, or many, are molecules that are found naturally and have been found to have biological effects, but we can't extract enough of them from nature to meet our supply. So we find synthetic ways of making the same molecule, and we've shown many, many times that these same molecules will have the exact same impact biologically when we take them in. Biology has no way of distinguishing between two molecules if they have the same structure. All right. So this is vanilla natural. You can make some of it. Vanilla, when it was first brought to Europe, I think it was around 200 years ago, was a smashing success. Everyone was very enamored with the smell and the flavor of vanilla when it was first brought from tropical regions to Europe. And very, very suddenly, the demand for vanilla outstripped the supply for vanilla. And so what enterprising chemists decided to do almost right away was try to find ways of producing vanilla from some other source. And I have in my hand here a bottle. I'll bring it up close to the camera. And you can see this just looks like a bottle with some random white substance in it. This is full of vanilla extract. If you were sitting in front of me right now in person, I'd take the cap off and you could smell it, and you could believe me that this smells exactly like, vanilla from vanilla ice cream or whatever. This is artificial vanilla extract that I have in my hand. It was made from an artificial source, and this is where artificial vanilla extract can come from if you buy it in the store. So the first method people found to produce artificial vanilla extract actually started with cloves. Cloves was another, at the time at least, more widespread. I don't know if it's a spice or a seasoning or a whatever. But anyway, cloves contain a high content of a molecule called eugenol, which the structure is shown below, which is similar but not the same as vanillin. Chemists found a way to take the eugenol out of the cloves, basically press them and get the oil out, and then chemically convert it in 2 steps to vanillin. So they found a way to increase the supply of vanillin, to make the same molecule artificially, although from a natural source. This process can basically produce vanillin at about 1/4 the cost of actually growing it directly yourself. So this was actually very welcome at the time because it certainly helped meet the demand for vanilla right away. There's actually been multiple, there's been an evolution in how we produce vanilla artificially since those early days. There was actually a period of time in the 1980s where something like 85% of the world's supply of artificial vanilla came from Canada, and it came from a single plant in Quebec somewhere. And this was actually a pulp and paper plant, and the pulp and paper plant had a byproduct that could be chemically converted to vanillin, and so this was where we got our vanilla from. It was a byproduct of pulp and paper production. Since then, the methods used to make pulp and paper have become more green, and as a result, the byproduct was no longer present, and so we've had to find other ways to make vanilla. And so currently, if you go buy vanilla extract, And it's basically alcohol solution with artificial vanillin added along with some colors. And the original source of this vanillin now comes from crude oil. So crude oil is taken, there's a molecule in crude oil called benzene, and benzene is a pretty harsh carcinogen, but you can chemically modify benzene from crude oil to make the molecule you see on the bottom left here. That molecule is called guaiacol, and guaiacol is another naturally occurring compound that is produced when you roast coffee beans, and it contributes to the flavor of like freshly roasted coffee beans. So that can be made from crude oil. A few more chemical steps later, and we have artificial vanillin. And because crude oil is quite cheap, benzene is quite cheap, you can produce large amounts of this molecule very cheaply. And it's identical to the compound that you get from the natural source. There's no way of changing, distinguishing between the two. Now, when I say these are identical, if you buy artificial vanilla extract versus natural, and I'm sure if there's any bakers in the crowd here, people may argue with me that, oh no, the natural stuff is much better, and it might be better, because what the natural vanilla extract does is it extracts a lot of things out of the vanilla beans, not just the vanillin. So there could be other sort of minor contributors to the flavor, which overall makes the product a little bit different than the artificial, in which case you may prefer natural or artificial. I guess what I'm saying, so if you do taste a difference between artificial and natural, that is real, right? There is a difference between them. But what I am saying is that in terms of, safety, if you're buying natural vanilla extract because you think artificial means chemical, means lab, means unsafe, that's simply not true. Okay? So that is the difference between the natural and the artificial. We're all good so far. One thing that I do want to point out as well is that when a substance undergoes a chemical reaction, it'll make a new chemical that doesn't necessarily share any of the properties of the original substance. We talked on the previous slide how you can start with benzene and turn benzene into vanillin. Just because the benzene is carcinogenic and started out, that was the source, doesn't mean that the final product is somehow still carcinogenic or that it carries any of the properties that you find with the benzene itself. So this particular slide shows two substances. Sodium metal. It's a kind of a soft metal. You could squish it with your thumb. If you drop it in water, you can see it's very reactive. It sputters, it catches on fire, it makes hydrogen gas, and reacts very, very rapidly. In the right, we have chlorine, which is a very, very reactive gas. It's used to kill things in things like swimming pools and in water supplies. If you mix these two together, they'll react with each other to produce sodium chloride. And sodium chloride itself has none of the properties that the original two substances had. Sodium chloride will dissolve, it's listless, it'll dissolve into water and just make salty water. Doesn't make fire, doesn't explode, it doesn't do any of those sorts of things. So when a chemical undergoes a transformation, the product doesn't necessarily share any of the features that the product has. So to say a chemical is dangerous because it was made from X, Y, or Z that was dangerous, that argument doesn't hold any water in chemistry. By the way, there's a new way of making a vanillin. It's a newer method. It starts with rice bran, and rice bran is a waste product when you grow rice. It has kind of a fibery covering, and it's separated from the rice that's sold to us for the most part. And you can take this waste product and you can treat it for about 50 days with a very specific strain of bacterium. And after 50 days, per liter of this sort of slurry you have going, you get about 6.5 grams of vanillin. And so you can make vanillin artificially using this particular process. This, by the way, produces vanilla that's roughly 20 times more expensive than the vanilla produced by the crude oil. Yet, this process actually has economic viability. And the reason, even though it's so much more expensive to produce vanillin this way, it's because this vanillin can be marketed as a natural flavor. Vanillin produced by the plant also can be marketed as a natural flavor. Vanillin produced from crude oil or from the cloves or from any, the other process we talked about, those are called artificial flavors. And this is where the definition comes from. This is not a scientific term, this is a marketing term. It's called a natural flavor if all of the chemical steps to produce it took place inside an organism. If any of the chemical steps to produce it happened outside of an organism, then it's an artificial flavor. So the chemical produced inside the plant is a natural flavor. The chemical in this example is natural because it's produced inside the bacterium. So if it happens outside, like in a flask or in a factory or wherever, then it becomes artificial. And marketing, if you're trying to market foods, and one says natural, all natural, or natural flavors, or things like that, that can mean big dollars. So it's important to certain people when they advertise their foods, whether it's natural or artificial, even though that they're identical, even though that it'd be hard to argue that the process you see on this slide is a natural process, or that it produces a product like you would expect to get from the natural extract from the plant. But that's marketing for you, and marketing doesn't always necessarily reflect reality or science. And hopefully in this course we get to dig into that a little bit more, and we dig into some of these differences between how things are portrayed in the media and how things actually are. Okay, I'm going to finish my coffee here. Cold. All right. So, takeaway message from this little piece then is that if you have a synthetic copy of a natural compound, they are not more toxic, they are not different in any way biologically. Okay, there's no difference from the biological impact there. The biological activity of a chemical depends on its molecular structure, not on its origin, not on the process used to make it, not its source, not its history, none of those things. All that matters is where it came from. Same argument as GMOs to an extent, and I would agree with that as well. All right, so we have another question. Vanillin is the molecule responsible for the vanilla flavor and smell. Chemically speaking, how is vanilla molecule produced by the vanilla plant different from a synthetic copy produced in a lab or factory? The version produced by people is safer because it's artificial. They both have the same structure, so they have identical chemical properties. The version produced by the plant is safer because it's natural, and they have different structures, so they have different properties. And the answer here is B. When I say it's B, by the way, one thing I'm going to say is that the order that these answers are presented will vary from person to person. If you're following along, you may not have A, B, C, D with the same, B may not be the right answer for you. It could be the same answer, but it'll be D or whatever. They're randomized. So don't necessarily put the letter I'm putting down. Make sure you understand why the answer is right, and select the right letter based on the individual quiz that you get when you open it. Okay, 2016, the Royal Society of Chemistry, RSC, did a public survey in the UK, and they asked, I don't know how many people, lots of people, the following question. Natural chemicals are safer than man-made chemicals. To what extent do you believe this statement? And what you can see is 11% strongly agreed that if it's natural, it must be safer than a chemical that's man-made. 30% tended to agree, and so the overall positive here was 41%, approaching 50% of the population would agree with this statement. Tend to disagree was 27%, strongly disagree was 17%. That 17% may have taken my course, and then 15% somewhere in the middle don't know. And so that's a pretty actually astounding statement. I mean, maybe it's not surprising, right? Like, the way chemicals are presented as these dangerous things that we need to be worried about, we need to reduce our exposure to, and all these sorts of things, maybe this isn't a big surprise at all. But hopefully, after the unit we just looked at on vanilla, you may agree with me that this statement is not correct. So there's a whole industry around this, by the way, which is that of organic food. And if you want to go to the grocery store, many items of produce have organic and non-organic versions. The organic versions are generally more expensive by, 25%, or I guess it depends item to item. And organic items are universally presented as the healthier option. And one thing that's actually interesting is, I used to believe this, that organic food meant it was grown without any pesticides or herbicides or anything like that. It turns out that's not true. What makes organic, and we have a unit on this later on in the course, what makes a substance considered organic is not whether it uses pesticides or herbicides, but what the source of those pesticides and herbicides happens to be. If it comes from a natural source, then it's considered organic. If the exact same substance came from an artificial source, it's not considered organic. And it turns out that whether a pesticide is natural or synthetic, they have similar safety profiles. There's no dramatic difference. Just because something is natural does not mean it's safe. And so a lot of the marketing around organic is actually misleading. Now, I'm not going to say that organic is a total waste. Like organic, it's a very broad and complex issue. There's many different types of food. In some cases, organic might have advantages. In some cases, the synthetic or the non-organic might have advantages. There's a lot of very different things wrapped up in this. One particular food, organic may make some sense in some areas where it's grown, not in other areas, and so on. So it's a very detailed and nuanced topic that we can't really completely delve into. But this whole idea, what defines organic food is the origin, whether it's natural or synthetic, of the chemicals used to treat the plants as they're growing. All right, so you may recognize this person, Gwyneth Paltrow. She is famously, what's the character's name? Pepper Potts in Iron Man. And she says this: I don't think anything that's natural can be bad for you. So, it's a pretty loaded statement. There's all kinds of things that are natural and that are bad. Like, obviously, like, there's animals that produce toxins that are natural and very bad for us. Black widow spiders as well. Cobras produce toxins that are also really bad for us. And this little guy, cute little octopus, I think it is. This is one of the most toxic animals in the world. This produces a toxin that can kill you very quickly. So there's lots of substances that can be found in nature that are obviously very bad for us. Here's an ad for 7-Up. Now 100% natural. And you can see it's, shown growing from a tree. Presumably the lemons and the limes, natural ones were used to flavor this thing. Presumably the sugar, I don't think there's such a thing. Well, I guess there's artificial sweeteners, not artificial sugar. But this is obviously presented as an advertisement to give the impression that 7-Up, because it's natural, is now somehow healthy, or healthier than some other hypothetical drink that's not natural, or doesn't contain all natural ingredients. And this is where it's a bit of like, I don't know what the word to describe this would be, but they are using this concept, this public fear of chemicals or synthetic substances, to promote their product as being a healthy option. Where, if you drink lots of 7-Up, whether it's natural or not, by far the risk to your health is not coming from the fact that it may contain some synthetic flavoring agents. Definitely it's because it's loaded with sugar, right? There's other reasons why this could be bad for you. Yet this is very ubiquitous in marketing, especially nowadays marketing of junk food. Presenting a junk food as being all natural or organic or whatever, as if that makes this now a healthy choice. Here's a good one I found. This is 100% additive-free natural tobacco. And of course these are cigarettes. As if somehow these cigarettes are now a healthy choice, right? They used organic tobacco, organic menthol, etc., etc. So somebody mentioned in the chat earlier on about how vanilla is related to beavers, right? And we can. So this is person pictured here is her name is Vanny Harry, and she titles herself the Food Babe, and she has a website, foodbabe.com. She has, I think she started out on Facebook, and she presents herself as a nutrition researcher. She doesn't have a background in nutrition. She doesn't have a background in science. I think she's got a IT degree, but she's since started this basically online empire where you can go to her website. And she writes these articles every so often where she'll basically what she does is she'll find some product that's produced by some well-known business, and she'll attack it for some chemical substance that it contains. And here's one. The title of the article was "Do You Eat Beaver Butt?" And she says, "I couldn't believe there was beaver's ass in my vanilla ice cream." And so what she did is she talked about a chemical that is actually produced by beavers, and beavers have these little glands near their anus, and these glands produce a chemical called castoreum. And castoreum, it's used by the animal for marking its territory and things like that. It's a very highly potent, smelly kind of scent that it can produce. And what people recognized is that if you take this substance, this oily substance produced by the beaver, and you dilute it, it can have kind of an attractive flavor or smell. And for many years, beavers were hunted for their pelts because their pelts can be turned into felt, which was popular for, I don't know, a few hundred years ago, I guess. But what they were also doing is harvesting these scent glands near the anus of the beavers, and you could take the chemical out, and you could extract the chemical, and it was used mostly in perfumes. This stuff is actually very expensive, and apparently, and I've never smelled this directly, but if you dilute it to a certain extent, it has a vanilla type flavor and smell with kind of, like people say, overtones of like raspberry. So it's a very pleasant kind of smell. So this stuff is almost all used in the industry for perfumes. Very, very expensive compound. If you wanted to use this in ice cream, it's actually allowed as a natural food additive. So what the Food Babe is complaining about is the fact that there's this seemingly very disgusting substance. It's technically not from the beaver's ass, but it's nearby. That could be present in something like vanilla ice cream that you buy. It turns out that, the amount of castoreum you would need to flavor a half gallon of ice cream, which is like a 2-liter bucket, would cost around $120 just for the flavoring alone. So if you buy ice cream and you've spent less than $120, you can rest assured that there's actually vanilla in your ice cream and not this castoreum compound. But if you have perfumes, and in particular high-end perfumes, it very likely maybe does contain this. Perfumes can become extremely expensive, by the way. There's very cheap ones that you can buy, but the really expensive ones, one reason why they're expensive is because they may contain very rare substances like this castoreum. All right, so here we go. Food Babe. I'm going to talk about the Food Babe just a little bit and wrap up this class because we only have about 6 minutes left. So the Food Babe basically has a blog where she basically does these so-called investigations into food. And she has some gems, some quotes. This is one. She says, "There's no acceptable level of any chemical to ingest ever." And this is a pretty ridiculous statement if you consider all matter, like air and water and so on, as being chemicals. But even as a synthetic chemical, the idea that there's no acceptable level is also a little bit wild, as we will see in our next unit on toxicity. She also says this: if you look at the ingredients in food, if you can't spell it or pronounce it, you probably shouldn't eat it. And she didn't generate this idea. I've heard Michael Pollan, who's a popular writer in topics of nutrition. Omnivore's Dilemma, I think, was one of his big books. I think he originated at least this concept before her. But it's this idea that, looking at an ingredient list, if you don't know what's in there, don't eat it, right? Which implies that any chemical that is an unrecognizable thing in food is somehow dangerous. It kind of defines too what she means by chemical here. She would define a chemical as any ingredient in food that is not recognizable, not easy to pronounce, has a big long sounding chemical-y name. It turns out though, if you look at natural foods like bananas and eggs, it contains all sorts of things in there, like phytosterols, palmitoleic acid, dodecanoic acid, and so on, which are present in all of these foods. And of course, these were not put here by people. These were naturally put in there by the banana plant or the chicken, in the case of the egg. So again, a bad metric to determine the safety of a chemical is how recognizable the name is, or how easy it is to pronounce, or how many syllables there might be in the name. This picture on the left is actually taken from the outside wall of the A&W in New Minas. Now, this sign has since come down. In fact, the frame is still there, just the picture's gone. And A&W is presenting their food as a natural choice. If you can't spell it, you shouldn't eat it. That's my rule. The beef raised without the use of hormones or steroids. Again, it's using this public fear, this public perception that synthetic chemicals are always bad to promote their food as a healthier option. And A&W makes good food, sure, but is that food you see pictured there by A&W any safer than an equivalent meal from someplace like McDonald's, for example? And I would argue no. They're trying to promote their food as a healthier option when in fact it isn't. Question 4, what is castoreum? A drug used to treat cancer, blah, 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 blah. Of course, the answer is D, or at least D in this version of the question, a substance produced in glands near the anus of beavers used in perfume and potentially as food additives. It's allowable to be used as food additives. All right, I'm going to stop here. I'm going to come back to the Food Babe when we meet again on Thursday. Look out on our Acorn page for our link for our next class on Thursday. If there's anything you'd like to see in the course or any comments you'd like to make, please feel free to get in touch, drop me an email, and we'll see all of you again next week. Awesome. Bye-bye, and see you on Thursday.